purpose of this video clip is to explore the role of chemistry in fluid dynamics. So fluid dynamics is a discipline that studies the motion of fluids as well as the interaction of the fluid flow with the surrounding. Fluid dynamics is everywhere in our life, and in fact, for example, hurricane is basically a classical fluid dynamics problem. And if you threw an olive into a cup of cocktail, then you see this beautiful splash, and that is also a classical fluid dynamics problem. And even if we just breathe, then we actually inject a jet into the surrounding air, and that is another classical problem in fluid dynamics. So fluid dynamics can be very useful. For example, design engineers can study the airflow near a speeding car, and that can help us to decrease the drag experienced by the race car, and hence we can make it go even faster. And fluid dynamics can be just also purely fun. For example, we could study the air flows near a running dinosaur and envision how much drag this monster actually could experience at the top speed. And if we have a cup of afternoon tea, we could also wonder what would the flow near a slice of cake if we have a gentle breeze brushing our cake. So by and large, fluid dynamics has been studied and practiced for thousands of years. And most of the time, we focus on microscopic behavior. And it's fair to say that the classic fluid dynamics say neither individual molecules or their interactions. And this can be appreciated by looking at the governing equation of fluid flow, which is the Navier-Stokes equation. So here we show a Navier-Stokes equation for a classic Newtonian fluid. And on the left-hand side, we say the mass time acceleration term. And on the right-hand side, we say the various forces responsible for driving a flow. So now the key thing that you can observe from this equation is that the nature of the fluid actually are entirely encapsulated in two numbers. One is density, and the second is viscosity. So here we really don't see any individual molecules as well as interactions between these molecules. They are all hidden, packed, or encapsulated in these two very simple numbers. This is in stark contrast to chemistry. So in chemistry, most of the time or a lot of times, we are very interested in molecules, right? So how atoms are bonded to each other, and how if we have one molecule here, say for example, lithium ion that is chelated by a very complicated molecule like this, right? So how their electron cloud actually will interact. So hence, really one key element or key aspect of chemistry that we really oftentimes are looking at individual molecules, their bonding, their interactions, and we care about specificity. And that is, if we have molecule A and we have molecule B, the shape and the size and how atoms are arranged make a great deal. And chemists are very obsessed in studying this kind of thing. And this is actually can also be appreciated by looking at the fundamental equation in chemistry, and that is the Schrödinger equation. So in this equation, both the wave function as well as the Hamiltonian are mostly, right, so people solve them or define them, explore them at a subatomic scale, right? And so here, really, the focus is a lot of time. It's at the kind of the atomic level, right? So here, things are very much oriented towards single molecules, or a lot of time. So now we say that on one side we have fluid dynamics where we really don't see individual molecules, or we don't care about their interactions as long as we get our density or viscosity correct. Well, on the other side we have chemistry that is relentlessly focusing on molecules and even smaller electrons. So it's fair to say that fluid dynamics has been largely separated from chemistry in the past. So this actually have served us very well. For example, a design engineer, when he tried to optimize the flow near a race car so that we can reduce the drag, right? He or she does not have to worry about the size and shape of the oxygen and the nitrogen molecule, and even less so about, say, for example, the vibration of the atomic bonds. So however, in the past decade or so, a lot of progress has been made in engineering practice that has significantly pushed the envelope of fluid dynamics. And this actually has forced us to take a look at the traditional paradigm where fluid dynamics is segregated from the chemistry. So in a series of videos, we would like to explore the role of chemistry in fluid dynamics. In this video clip, we explore the importance of chemistry in water imbibition in clay. So one of the most important developments in petroleum engineering in the past several decades is the shale gas extraction. So shales are essentially very tight rocks with very tiny pores that trap either natural gas molecules or oil molecules in them. So there are vast supply of shales around the world, but traditionally it has been very hard to extract the hydrocarbon trapped in this kind of shales. And in the past several decades, however, people developed new techniques to extract this gas. So the idea here is actually quite simple. So what you do is you drill very deep into the geological formation where you can reach the shale, and then you pump millions of gallons of water or fracking fluids into the formation, and this will force generation of cracks inside this formation. As such, this very tiny crack will create a pathway for the gas or oil molecules actually to go out and hence being extracted. So one of the major concerns for shale gas extraction is the potential pollution of the water, drinking water, by the fracking fluids. So the idea is that there's so much water actually goes into the ground, right? So where would they go? And indeed, experimentally, people found that very little of the water that we pump into the ground actually comes back. So this brings even more worry to people. So however, one of the important hypotheses that emerged over the past years is that the water actually are not going into the water table as some people have worried. Instead, they got trapped into the shale. So it's important to recognize the shale actually are strongly heterogeneous materials. In addition to the organic matrix that store the gas, there are also minerals, say for example mica, actually trapped inside the shells. So when water actually meets mica, this kind of hydrophilic mineral, so they actually get imbibed into this kind of minerals pores. So as such, they actually store the water there and they will never make to the water table. So this kind of phenomenon actually can be described using the classical fluid dynamics. And indeed, if we have a micropool here, right, so that whose surface actually is hydrophilic, and now if that is exposed to the water, so now because of the interfacial effect or the surface tension effect, there will be a capillary pressure generated using this according to this formula. So now if the capillary pressure is higher compared to the gas pressure, then classical fluid dynamics will predict an emergency of what we call the capillary flows. So this capillary flow will pull the water molecule from the environment into the pool, as such store the water there. So of course the question you could ask is that, is this a kind of accurate description of the phenomenon? Well, to a very large extent, yes. So in fact, in addition to a direct experiment, right, we can check the prediction of the classic hydrodynamics using molecular dynamics. So the idea here is that we explicitly resolve both the water molecule as well as the mineral pores, right? So in this case, although we are not really capturing all the chemistry of the materials involved here, so we are capturing some chemistry, for example, water molecules, the size, shape, and the fact that they are dipolar, and the fact that they interact very strongly with the surface of the probe. So if the gas pressure inside here is very low, and in this case, the gas pressure here is 0, and then if we run simulation, indeed we find the fluid inside the reservoir here actually being pulled into the pool. So as we can expect from a classical hydrodynamics. So this, of course, is just one scenario. So another scenario that we can possibly encounter in practice is what if the gas pressure inside here actually is comparable to the capillary pressure. So under this condition, the classical hydrodynamics will predict that there will be no capillary flow because the driving force for fluid transport into this is not sufficient to overcome the gas pressure. So in this case, basically water will not imbibe into here. Of course, water can still evaporate at the meniscus and then goes into here. But for very small pools, this is a very slow process. So what would actually happen if we consider all the chemistry of both the mineral surface as well as the water molecule? Well, we can run a simulation and find out. So what we say is that in this case, initially the gas pressure here is pretty high, and then once we release the water, the gas will goes out, and such the pressure became lower. So in this case, the capillary pressure, however, is still not sufficient to overcome the gas pressure here. So we don't see a box flow like what we saw in the previous slide. Instead, we saw water molecule nevertheless actually can go into the pool as some sort of thin layers. So we can look at more carefully at this thin layer by focusing on a few strips. Right? So what we say is that we have 4 strips here, A, B, C, and D. And we plot the density of water molecule in the direction normal to the surface. So what we found is that very quickly, the surface water actually at strip A became reached a steady state, and then gradually, as the water molecules spread on the surface, right? So D actually start to have water molecule, and then it gradually reached a thicker layer. So, but in all of this case, what we found is that the water molecule actually spread onto the mica surface as a single monolayer. So this is a phenomenon that we can call the surface hydration. We can certainly not call it as the capillary flow because we don't see a bulk flow. And so what is causing this kind of non-classic hydrodynamic behavior? Well, it turns out that this is very closely related to the chemistry of the mica. So mica is a very strongly hydrophilic mineral. So in the sense that if you bring a water molecule right to a mica surface, if you compute its potential energy, we find that this potential energy is very low, meaning that water molecule will favor mica surface. And in fact, this energy is even lower than the interaction energy of water molecule in the bulk. In another word, so mica is such a hydrophilic surface that water molecule like mica even more than a water molecule. So another interesting fact is that a water molecule, if it forms a single layer on the surface of mica, because of the strong interaction between the mica and the water molecule, it is such that an isolated water molecule has lower potential energy compared to a water molecule in a thin layer. So what this means is that a water molecule will have the tendency to actually jump away from this water layer or water film here, so that it could be energetically even reach an even lower energetic state, which is always oftentimes favored. So now we can say that the chemistry of mica actually can play an important role in the formation of this kind of phenomenon, and that is surface hydration. So this kind of thing actually can be described using a mathematical model. Some people developed over 20 years ago. So the essence of this model is considered a jumping of water molecules along the surface, and this model will consider interaction between a water molecule at the front with the surface and surrounding, as well as in the bulk, as well as in a film. So now a key prediction of this model is that the length of the water actually spread into here is actually grows with a t to the square root. And that is the length of this will grow diffusively from a physics perspective. Importantly, what this model says is that the effective diffusion coefficient of this kind of growth is not just the diffusion coefficient of water molecule on the surface. Instead, it's amplified by this factor called A sub m. Now, if the interaction between the water molecule and the substrate, or in this case, solid wall, is very strong, then A sub m actually can be much larger than 1. So is this something that we see in our simulations? Well, indeed so. So what we show here is a plot of the spreading of water molecule on the surface as a function of time. What we see is that the spreading length to the square scales linearly with the time. In other words, so h would scale as a square root of t, as predicted by the model. More importantly, by fitting this curve to a linear curve, we actually can extract the slope, and from that we can extract the effective diffusion coefficient. What we found is that this effective diffusion coefficient of the growth of this spreading water thin film is actually almost 12 times higher compared to the diffusion coefficient of the water molecule on the surface. So what we can say is that the chemistry of the mica, and that it's such a strongly hydrophilic material that interacting so strongly with the water molecule, actually can fundamentally change whether a water molecule can go into the pool if the capillary flow is suppressed. And more importantly, it can choose how fast this kind of water film will spread. So this again reminds us of the importance of chemistry, in this case the chemistry of the mica in fluid dynamics. So if you are interested in exploring the ideas shown here in more depth, you can read these two papers. So in particular, this model, which was published more than 20 years ago, actually turns out to be very important to understand the chemistry and the fluid dynamics that are revealed here. With this, I will stop here. Thank you very much for your attention.